right. So what we're going to talk about today is probably the basis of all our work in the engineering department, load calcs, right? But specifically, this presentation, we're going to talk about how we perform load calcs, and the way we do that is through trace. So I know a lot of us already know how to use trace, and you maybe even started using trace before you even set foot at SVM, or it's brand new to you. But the goal of this presentation is to do a step-by-step walkthrough for a load calc using Trace 700. And I know this is pretty rudimentary, it's pretty basic stuff, but it is really necessary for us to document this, to standardize our approach and the way we do load calcs, to not only help ourselves when we do our job, but pave the way for future engineers and new hires. So this is a good opportunity to review the basics if you already know what you're doing, and if you're brand new, this is going to be the perfect video for you. So even if you think you've mastered the basics, there's always still more to learn, and only when you've actually begun to master the fundamentals do you even realize that you were never even a master at all. You're always going to be a student. So anyway, enough about my soapbox. Let's get back to load calcs, which is the foundation for all that we do in engineering. So, what are load calcs? To make sure we're all talking about the same thing when we say load calcs, here's a quick definition. Load calcs are predictions of the required cooling or heating to condition a building throughout the year. They're predictions. And we design HVAC systems to meet the loads of the building. So a couple of basic questions we'll start off with are, how do we measure energy required to heat or cool a room? Why do we use Trace 700? And what should we be aware of? So how do we measure energy required to heat or cool a building? In America, we measure that in something called British thermal unit, which I know it's strange, we're in America and British, but blah, blah, blah. But that is the unit of the measure of energy, the amount of energy required to heat 1 pound of water 1 degree Fahrenheit. And since we're dealing with such large systems, most of the time, a lot of the system measurement will be in terms of tons. And 1 ton, not in weight, but in terms of cooling, is 12,000 BTUs. And here's an example of saying how much energy would take to melt 1 ton of ice. It would take 12,000 BTUs in 1 hour. So, why do we do load calcs? Why do we do them at all? Well, my friends, that's because we are in the science of comfort. This is what we do. The average American spends 90% of their life indoors, and because of COVID, it's probably more like 99% for 2020. But because we are working and living indoors most of our lives, ensuring that people are comfortable where they spend a significant fraction of their lives makes an important and impactful industry. And I'm going to get on my soapbox, you already heard it, but this is really important stuff. Because being comfortable is more important than we think because it impacts our mood and our work productivity. So this semi-Venn diagram on the right here illustrates the concept pretty well. It factors things that influence us like our environment, the kinds of clothes we wear, and what we're doing. And what's circled in red are things that we can control, things like thermal conditions, humidity, air quality, acoustics, specifically in our industry. And so everything that we do impacts human comfort. And we do our best to control the environment. And the way we model that is in Trace 700. Quick tangent. In work and in life, there are only 2 things you can control: your attitude and how you react. Pretty profound stuff, if you ask me. Okay, so the 3 objectives we're going to hit today. 1, we're going to learn the sources of heating and cooling in a building. We're going to learn how to perform a load calc in Trace step by step, and we're going to avoid garbage in, garbage out. And we'll get to that later. So here are all or most of the heating or cooling sources in a building. There are things outside like the sun, lack of sun, weather. If you're inside, people emit heat, lighting emits heat, certain appliances or other equipment, which is often referred to as plug load. All of this adds or removes heat to the system. And the system we're talking about is the building. And we need to take all these sources and measure them in terms of BTUs. Couple things to note, lighting is typically measured in terms of watts, so we can convert that to BTUs knowing that 1 watt is 3.412 BTUs per hour. And horsepower is often used to show that 1 horsepower is 746 watts, and then you can convert those watts into BTUs. Anyway, no matter how it's measured, all of those things we need to show in Trace to perform our load calc. And Trace is really good at helping us with that. And I like to think in terms of BTUs typically all the way around. So let's talk about Trace step by step. This guide will make sure that all your bases are covered. And we'll go over each step briefly in this presentation. Trace is an incredibly powerful tool, and it makes our job so much easier. And what makes Trace so powerful and smart is because of you, because of us. The intelligence comes from you, not Trace. You have to communicate what you know so that the software does all the heavy lifting for us. So you can think of the big picture. So let's get into it step by step. Number 1, create a zone plan. The first step, you should already know how to create a zone plan. But make sure you measure the square footage of each room and zone and measure the exterior dimensions. The tricky part for Trace and even ourselves is to determine the orientation of the building. And you can figure out the orientation of the building using architectural drawings or simply using Google Earth or Google Maps. And whenever I do a zone plan, I always draw a compass that is relative to the plans, and then global, like the actual north, south, east, west. So that helps me really understand the orientation. So there's 2 ways you can do that in Trace, which is global rotate or manually insert the degree in which the wall is facing. We'll get into that later, but just do what's best for you. Second step is to determine the location and acquire your weather data. This world is a beautiful place, and each place has beauty for different reasons. Oftentimes, that reason is probably weather. You can have warm weather on the beach or snowy, cold weather in the mountains, but it depends on where you are, and Trace needs to know that just as much as you do. So to get an idea and to get that data, ASHRAE has already done that for us. So the ASHRAE 2019 weather data, which is also just Title 24 JA2, we can obtain the dry bulb and wet bulb temperatures for heating and cooling depending on the season, typically summer or winter. So meteorologists already gathered the data, and now we get to use it. So the screenshots shown here show you exactly how to pull and place the data in Trace. Third step, create room or space templates. So templates in Trace are basically cookie cutter designs. They are patterns used throughout the building that you can set up front and apply to various rooms and zones. Templates are divided into 5 categories, which are shown here. The internal loads, where you can insert loads from people, lighting, and equipment. Your airflow, which you can stipulate how much ventilation is needed for a specific room type. Your thermostat, which you can set specific set point temperatures for a space. Construction, where you can itemize the thermal properties of windows and walls that will be installed. And the biggest cookie cutter, which is room type, where you can use the combination of all the templates listed above to make a bigger template for a specific room type, say a kitchen or a lab. So here's what all that looks like in Trace. All you do is input the number of people, lighting, and miscellaneous loads for each template in the highlighted portions on the right, and the 2 tables shown here are typical internal loads as well as a range of heat load generated by us, human beings. So our bodies naturally, even idle, standing still, exert heat, and that intensity of heat varies depending on what we do. Are we standing, walking, running, exercising, and so on. So next on the templates is airflow and Tstat. These are the next 2 cookie cutters, which allow us to set ventilation rates in terms of CFM per person, as well as design set point temperatures for common spaces. You get to adjust for relative humidity and drift points here as well, and most of the criterion is stipulated by the client, but the table above shows the most common design values that we use. The next cookie cutter is construction. This is where you input insulation and heat transfer properties for windows and walls for the building, for example, like U values and shading coefficients. And these are typically difficult to track down and get the actual numbers, so we have to make assumptions here sometimes. And the basis of our assumptions come from Title 24 JA4 and CEC section 110.6, where they list thermal properties for various windows and walls. And the table shown here is a post-2001 construction remodel as an example. And the screenshot on the right shows you where to input these values in Trace. The last thing for construction templates is the height of the floor, which is typically assumed for our practice to be a 2-foot plenum with maybe 12-foot floor to floor. Typically, the first floor is a multi-story building that has higher ceilings, so look out for that. All right, U-value and shading coefficients. I wanted to throw this slide here to recap the difference between the two. Just remember that the lower the U-value, the better the insulation, and the higher the shading coefficient, the higher the heat gain is into the space. So you can refer to this slide for reference if needed. Energypro. So another thing we need to include here, just in case to justify your assumptions, is to check your U values and shading coefficients using this software. This software is used for energy modeling, but it's also a really great tool for verifying construction properties. So here's an example of a wall built around 2001, as well as a window for reference. And here's the other one. And the last cookie cutter template is the biggest one of all, which is the room template. Here you can apply all the previous templates and make one giant template for a specific room, for a conference, kitchen, lab, and so on. Personally, I don't use this feature as much, but know that it's here and this is how you would apply it. Create rooms. The next main step is to insert the rooms and their properties into Trace. Now, typically, room in Trace we refer to as a zone. You can do this differently, but this is the way that I've been taught to do it. So we simply use our zone plan as your room plan for Trace. Insert the number of square footage, account for all windows and walls for the exterior zones, and count up the number of people and assign templates as you already created. So if you're dealing with a multi-story building, be sure to click on equals floor for the uppermost floor to account for the roof load. Otherwise, you'll miss a lot, and that's circled there in red. All right, next. Now that Trace has all your rooms and zones accounted for, we can now tell it what type of system will be serving those zones. And for that, we use the Create Systems tab. For us, given that we mostly work on commercial buildings, many of our projects will use VAV reheat with the 30% minimum flow, which is an option shown here in Trace. We can adjust things like temperature and humidity and set the maximum and minimum supply air temperature to 55 degrees and to 90 degrees, max and min, making sure you set both of those to max and min to the same value, because that removes the over-under sizing estimate in Trace, which likes to tack on as like a safety factor. It's a kind of contested point in the office. Some people like the over-under sizing, some people don't, but now you know how to remove it or keep it. You either set both of them to the same number or just the maximum to one number. So aside from the temperature, we need to indicate the appropriate static pressure for the fans, which typically ranges from maybe a 1/2 inch to 4 inch water gauge. And then the last tab on the right is Create Systems. And this is where you can apply system-wide diversity. For our case, just leave it as default unless the PM states otherwise, and that's in the coils section. All right. Next, we're going to do assign rooms to system. This is a pretty simple step. Now that you already have your rooms and you created your system, you just drag the room to the appropriate system. If you have multiple systems, then you might have to separate them, or you could just drag it all over to the one system you created. slight hiccup there. So now it's time to let trace do its job. Simulate the total amount of heating and cooling required to condition the building throughout the year. This is where all the magic happens, baby. But there are still a few things we need to adjust beforehand. So under the Load Parameters tab, adjust the cooling methodology to RTS, which stands for Radiant Time Series per ASHRAE, and the heating methodology to CLTD-CLF per ASHRAE, which is pretty much the approved design methodologies from ASHRAE that we use in our designs. And once that's all ready to go, make sure the checkboxes are checked under the Design and System area, then hit Calculate and watch Trace run its course, simulating weather conditions throughout the entire year. It's pretty awesome. And this is why Trace is so powerful. Now, we already calculated in Trace, but now we got to export those calculations. So we want to export the system, zone, and room checksums along with the peak cooling, peak heating, and load airflow summary in PDF formats first. And then after that, we want to export the peak heating and cooling and airflow summary as Excel data only. And the reason we do this is so we can examine, refine, and iterate our design by performing internal checks. Load calcs are an iterative process, and to see where we iterate, we use the load airflow summary and peak Excel data to spot check the results. The load airflow summary serves as a skeleton where you can extract the square footage and the people count, and then you replace the summary cooling heating data with the peak space sensible heating and cooling data shown here. In the upper right, you can show the heating and cooling delta T's and then use the sensible heating equation to determine how much CFM is needed to cool the zone, your classic Q equals 1.08 CFM delta T. Once that's all set, you can create two columns and check your CFM per square footage or your watts per square footage. And anything that seems high, maybe something greater than 5 CFM a square foot or 15 watts a square foot, should kind of raise a flag for you, and you should go back to see how those values came to be. And the last step is to document your design in the BOD. This is probably the most important step, is documenting your design, because as engineers, we're often asked to justify our assumptions or explain why we chose to design something the way we did. And this will help you keep track of what you did and help communicate to others what you did. So this way you're covered, the PM's covered, the company is covered, and the client knows what you did. This is an example of a few tables I put together for a project to clearly communicate my design conditions and assumptions. Common things to keep track are weather, design temperatures, indoor heating, cooling set points, wall, window, U values, internal loads per room type, and ventilation requirements. Not only is this good to say what you use, but it also justify where the values came from. So if it was a client standard, an SVM standard, Title 24 or CEC, providing a basis to show you have a leg to stand on, saying this is where my information is coming from. And then next, those are the 10 steps in doing trace, but now we have to understand and we have to do an analysis of the results. So this is what trace gives you in the end. We exported the calculations into a PDF, and these room or system checksums are the final product that trace produces, which gives us a global view of the entire system and a local view of each room or zone via these checksum sheets. And they have a lot of information. You look at this and it gets really, really daunting to look at and break everything down. So we're just going to look at the core components. This specific slide shows the heat transfer equations and techniques Trace uses to produce the values that are marked up here. This one's more detailed, but let's look at a simpler version. Let's start with the left side, cooling loads. It's pretty much broken up into two sections, envelope, which is your exterior load based on weather and building material, and your internal loads, which is based on people, lighting, and plug load. The sum of these loads is the total cooling load needed or heating load for the system or space. And this same technique is used on the right side for heating. So at a system level, it's really good to check the cooling coil selection data to see the total capacity, total BTUs, shown, which is in tons or MBH. This will help you size your rooftop equipment. So now let's do a practice exercise to kind of wake you all up and put our brains to work so we can actually appreciate what Trace just gave us. So what we're about to do is only a portion of what Trace does, but it will give you a sense of how powerful Trace is as a tool. So let's pretend you finished your zone plan. You have a 4-story building and the second floor looks something like this. Let's take a look at that blue zone in the bottom left. So all we're going to do in this exercise is to find the internal cooling load for the space and see how much CFM would be needed to take care of that load. Keep in mind this is just the internal load and we're not taking account the envelope or external load, which would need to account for windows and walls. We're just looking at people, lighting, and miscellaneous load. And since you already did a good job of documenting your design along the way, I went ahead and put up the BOD from tables from the BOD for you to use as a reference. Use the table to determine the internal load from people, lights, and plug load. Once you find the load, you can determine the CFM. Assuming the set point temperature of the room is 75 degrees and the supply air to the space is 55 degrees, how much CFM is needed to condition the internal space? So go ahead and do that calc by hand, pause the video, and take a look. All right, you should have unpaused the video, and let's check out the solution. So remember, this is just the internal cooling load. You should have gotten roughly 11,100 BTUs per hour and 515 CFM needed to cool the space. How did we get those numbers? We simply applied the relationships shown in those tables to obtain the BTUs. A common mistake is to forget to convert the watts to BTUs. Remember, 1 watt is 3.412 BTUs per hour. The calculations are itemized on the slide here, and the volume of air needs to be volume of air needed to cool the internal space. We simply use the sensible heating or cooling equation, which is Q equals 1.08 CFM delta T. Solve for CFM since you've already calculated the load Q. And then you can calculate the amount of outside air required per code pretty easily as well if you wanted to for extra practice. Remember, this does not account for your envelope load. It only accounted for the load generated inside the room. And this is where we're going to see why Trace is so powerful. Guess what? What you just did is a good way to verify your internal loads and load calcs. So check out that yellow highlighted box. That should match exactly what we did when we calculated the internal loads for the room. So now you know where those numbers come from. Where Trace comes really in handy is when it performs envelope loads. Trace is really good at calculating loads based on weather and construction material. So those calculations acquire a bit more work to do by hand. So Trace is a huge help here. And that's what you see in blue. Okay, so let's imagine doing what you just did for all of the zones for the entire building, then going back and calculating the envelope load for summer and winter conditions, and then some for every single day of the year. That is a lot of work, and that's a lot to keep track of. So that is why Trace is a really powerful tool, and it's the basis for all our designs in engineering. Starting outright and documenting your design will ensure your success for your project, your team, and your career. So that's just a lot to handle. So fast track. Sometimes we have jobs where we don't have enough time to use Trace because some are time sensitive and we have to iterate and make sure our load calc is clean and crisp. But if you're on a time crunch for a fast track job, here is a quick rule of thumb guide that can get you moving. These tables are itemized and estimated based on CFM values for a specific room type. The compass on the right is a nice tool for predicting envelope loads pretty quickly, and many of these are probably overestimates that came from common values in SVM's industry practice, so just keep that in mind if you're justifying anything. And if it comes down to it, you'll need to extend your project timeline to perform a trace load calc for a building or particular rooms, so you can let your PM or client know. Okay, where's the code? Speaking of justifications, most of the basis of our designs come from the CEC and ASHRAE. This slide points you to specific sections from those resources. Fenestration. Here's a table from the CEC that outlines typical U values for fenestrations, which is just a fancy word for glass, and you can use this as a reference. And here's a code section from the CEC that shows typical U values for walls and roofs, which you can also use to justify values in your basis of design. Where to look if you're not sure where to go? Here is a table that points out where you need to go based on the various categories you'd have to consider for load calcs, and you can use this as a reference as well. A couple buzzwords. One thing I just wanted to go over is commonly used words that come up when we're talking about load calcs. The next two slides you can use as a reference if you hear any engineering vernacular come up, but the main two I wanted to point out are sum of peaks and block load. Sum of peaks is the sum of the max load each room temperature experiences at different times of the day or the year. So a good way of thinking about this is if the sun were hitting the building from every direction. Now a block load looks at a building at one moment in time and tells you when the building will experience maximum load conditions, even if all the rooms are peaking. Not all the rooms are peaking, excuse me. So imagine the hottest day of the year around lunch hour. It's really hot. The building will need maximum cooling, right? More buzzwords, and there's where the sum of peaks and block load came from. Now some summary sheets. If you don't want to go through this presentation and you just need a quick guide because you already kind of know what to do, I've created summary sheets for our engineering onboarding program that outlines how to use trace step by step like we did in this presentation, as well as doing load calcs via fast track and analyzing checksums. So feel free to use these as resources as well. And if you learn best by watching videos, I've also made and have been working on video tutorials that walk you through trace and a simple load calc right on your computer, which you can follow, pause, and replay along the way. And with that, I guess thank you for taking the time to listen and watching this kind of long video. I know this stuff takes us back to the basics, but it's really good to review what you know, because like I said at the beginning, even if you think you've mastered the basics, you realize that you were never the master at all. You were always the student, always learning. So thank you and good luck on your job.